Okay, I think it starts. Okay, couple of things I want to say I think in before the class. Couple announcements. Some of you, several students, not many, 3, 4 students, 4, 5 students. I don't remember exact number. Still have a problem with internet or some issue with constant stable internet that can connect to the class. Okay, so since it's a small portion of the class, most of you I think is okay. I received your quiz submission. I grade 1 quiz. Seems like most of you it's kind of normal. Okay, normalcy for the online class like this. Okay, so for those, I just want to say, maybe they are even not here today, but I recorded and they may be able to watch the video. For those still have internet problems, I will try to find a way to help. But the thing is, this is a class, it's a junior level class, heat transfer. It's a very important class, okay? Just like all the other classes I teach. Eventually, you have to earn the grade to pass the class, okay? Even with a situation like this, I cannot hand you a grade without you conduct significant works, okay? So it's not possible. So you can count my words. It's not possible to say I'm not even come to the class, I didn't even take the quiz or didn't do much of project, then eventually Dr. Zhang, you give me a passing grade. So I won't do that against my principle. And I feel it's not fair to all of you can attend the class, okay? So I definitely won't just hand out a grade without you earning it, okay? Does that make sense? Okay, but how to earn it? I'm really open to discussion and I can help you. For example, if you really, I don't think many of you are like this situation. Really, more than half of the semester or most of the semester still couldn't get internet, or get something, cannot participate in the quiz and cannot do those projects. I'm really open to give an incomplete, okay? Maybe previously incomplete, you'd have to have a reason, right? Something like that. I think I'm open to that. And if really you only conduct 10% of the assignments, it's, I can't just give you a passing grade, but I really can give you incomplete when you have the constant internet and you can start to do those projects. All those quizzes, incomplete, we can do those things later, right? You can do in the next semester or even in the break, okay? So that's one option, okay? But see, that's for those constantly doesn't have internet, or maybe electricity. But for some of you, you have the internet. Just say, I have something else to do today. I cannot make the quiz. Then this is a different story. Okay, this is a different story. Okay, so try to make the class. See, we don't have final exams. We don't have midterm exams, right? So how do I control to maintain the quality of the learning? Okay, so I think I look into the participation a lot, because I think if you participate in the lecture like this, you learn something from it, right? And if you do the quiz with me and do solve problem with me in class, it help you save a lot of time of learning. And you actually learn it by doing those quiz problems and doing the experiment projects, right? So it's a different way to evaluate your learning. But I hope it's a more efficient way, and you can actually learn it. But without participating those activities, I don't see I can justify how well you learn the stuff. Okay, please keep in mind. And you can even tell your friend, maybe they don't have chance to watch this video or something like that. But just bottom line is you have to complete those assignments, okay, to make sure to earn the grade, okay? Show your effort and earn the grade, okay? Is that good? Yeah. I hope it's a difficult situation for some of you, but I hope I can still make it out and make it a fair situation. Okay. See, to me, I'm sitting here. I'm in the different shoe as you. You are just working on those things to pass the class or something like that. I have to keep 27 students here, be fair to everybody. Okay. The grading is a difficult thing for me for this semester. Okay. So the bottom line is you have to earn it. Okay, I have to show everybody earn the grade. Okay, so that's more comfortable situation. Okay, so having said that, I think I try to make a decision. So you still can miss some assignments and quizzes, especially the quiz. You know, quiz is in class. So I think I give everybody 2 opportunities. You know, 2 chances to miss. You can miss 2 quizzes. Okay, I should say for the reason like internet doesn't work or something, but I really cannot tell, you know, how do I know? So let's say I give everybody, you can miss 2 quizzes anyway, for any reason. If you just don't want to do that quiz, if you're too difficult, just go ahead, not doing it. Okay, but you have 2 chances. Okay, so is that good? So I think that's kind of okay. Everybody has the opportunity, so shouldn't be too bad. Okay, so yeah, I guess this is what I try to say. Any questions? Any inputs, any feedback from you? I'm open to, you know, discussion.
Yeah, I have a question, Dr. Zhang.
Yeah.
So, okay, I was looking at the project, and it just kind of got me thinking. We have, for our conduction, we're dealing with our Q value, our K, our area, our dx, and our dt. Okay, so
that's right.
Whatever we're doing it with, whatever material, we can find our K, and we can measure the area, and we can measure the thickness, and we can measure temperature. But how can we, so let's say I wanted to like predict the change in temperature or something, or maybe I find the temperature. How can I actually measure the wattage to like prove that calculations are correct?
If you use, that's it depends on maybe that's a limitation based on the availability of the equipment. But for the electrical heater, for example, okay, you should be able to see the wattage on the spec sheet. Okay, so that's basically the wattage it outputs. It's not 100% going into your material. Sure, I understand that, but it depends on sometimes you're doing experiment. That's a good question, actually. You're doing experiment, you're not in the ideal world. You're not gonna do the 100% accuracy on this, okay? But to me, as long as you know the error, you know the source of error, okay? If you can justify it, you say, hey, my experiment has 20% discrepancy comparing to the theoretical calculation. But see, I know the problem because the wattage coming out from the electrical heater, it's not 100% goes into the material. It lost something to the surrounding or something like that. Okay, so you justify it. As an engineer, you don't have to have perfect result always. But as long as you can make the story sound and justify the reason of some problem in there, you're doing as good as, you know, have the perfect result.
Okay, so
makes sense? So try the best you can. I'm not expecting to see all that. You match the theoretical calculation. But if you can have some quantitative measure in the similar, close, and you have certain percentage error that you can evaluate, maybe that's good enough.
Thank you.
Okay, you're welcome. That's a good question, actually. That's how, you probably haven't done many experiments in the curriculum yet. I don't know, maybe you did a couple classes. The experiment is it's not perfect, right? That's why experiment, you have so many issues, so many possibilities that can lead to error. They eventually, if you think, oh, 1% error is acceptable, then probably you're never gonna verify anything in the theory. Okay, so unless you have the $2,000 equipment, maybe you can make that accuracy. So it's really depend on the availability of your equipment. But for this project, I say less than $5 cost, then, you know, there's really a lot of limitation. But I want you to identify the limitation. If you see a terrible result, but you really need to identify some of the sources of errors. It's just not like, okay, I have 70% error, so that's it. That's what I got. I don't like that attitude, okay? At least you want to dig into the why I have so much error. It's possibility of this, possible of that, and then there will be the good project, okay? Oh, I have a question from somebody, from Toby. Say, hey, if we don't miss any quiz, of course, you know, if you don't miss any quiz, you drop the 2 lowest ones, okay? That makes sense, Toby? Okay. Good. Okay. Yeah, one person, one student is waiting. Okay. I guess that's the announcement. If you don't have any more questions, let's go into the technical part. Okay. So we'll continue on chapter 2. Last time we did we introduced the idea of the thermal resistance, right? So it seems like it will make the conduction, convection, heat transfer problem as a circuits. Okay, so you have a serial configuration, parallel configurations. Okay, then we can separately calculate the thermal resistance, just like electrical resistance. Okay, so then depending on the layout, you have the equation, right, to calculate the overall resistance. So then temperature difference divided by the overall resistance, then will become your heat transfer rate. Just like the 3 components in the electrical circuits: voltage, current, and the resistance. Same idea, okay? So I feel by using this way, the life of your calculation for those problems will be a little bit easier, I feel, okay? So last time is the Cartesian systems, right? XY coordinate system. Again, I need to introduce you the cylindrical coordinate. So in the real life, you're dealing with the circle cylinder a lot more than the just XY coordinate system problems, okay? So it's important. Always calculation will be more complicated for the cylindrical coordinates. The expression is longer, but still, I believe you can handle it. Okay, let me turn on my screen and let me show the whiteboard to you. Okay, can you see it? Not yet. Hold on. Participation. Okay. Okay. Now can you see the screen, the whiteboard?
Yes, sir.
Okay, good. So in the cylinder, radial system, they call it, right? To section 2.4 in the textbook. How do we calculate the thermal resistance for the cylindrical coordinate? Okay, so first of all, the equation. Okay, I think I spent like half class a couple of weeks ago derived the equation Q for a cylinder, right? Okay, so let me write it down the equation. It's 2 pi KL times T inner cylinder, inner circle, inner cylinder, minus the temperature at the outer cylinder, log, right, remember? R0 over Ri, outer radius over the inner radius, okay, for the 2 concentric cylinders. Do you remember this? A couple of weeks ago. I think probably you want to read the notes, refresh the memory. I think I have some homework problem using the cylindrical coordinate, right? Okay, so what is the thermal resistance? So remember, the idea is we convert this form into delta T divided by thermal resistance equals the Q, right? So the Q is supposed to be equals to Ti minus To over thermal resistance. We create this property, thermal resistance, right? Okay, so these two equations should be equivalent, right? So what does the thermal resistance look like? It will be just substituted in there, right? It will be log R0 over Ri divided by 2 pi KL. Okay. Similar to the cylindrical coordinate, I think. It's like what? What's, did anybody remember? Delta x, right? Delta x over what? K and times A. Okay. See, 2 pi L here is the 2 pi L times R is 2 pi R times L is surface area. Okay, it's a K area, right? So log become on top of it. Okay, and it's similar form. Okay, because this is a cylindrical coordinate, have to be right like this. Okay. Okay, then you can use the same form. Okay, so this is for a concentric cylinder. Okay, you have just like a pipe. Okay, the conduction in the pipe wall. Okay, the heat transfer rate in the pipe wall, conduction heat transfer rate in the pipe wall will be this equation, right? And this is the thermal resistance, and this is formed equation, right? Use thermal resistance. Okay. Does that make sense? Okay. So what about you have a pipe? You put an insulation out there. Let's say this is the pipe wall. This is the insulation. Okay, so how do we solve this problem? So you get the whole thing. Remember, if you were here last time, you know you're gonna have a temperature T in, the overall temperature here as T out. It's not the T in between, right? You treat the entire system as a whole, okay? In is the most inner temperature, out is the most outer temperature, okay? So your Q is T, again, T in minus T out divided by overall thermal resistance. Okay, overall summation. So is this a parallel or a series layout for the two resistance there, for the pipe wall as well as the insulation? You said the serial, right? Ti, To, okay? So this is R of RTH of the wall. This is RTH of the insulation, okay? So you just add them together. So the summation here is RTHW plus RTH insulation. Okay. So what is the RTH wall? Now, I think I use I and O temperature here. It's kind of like confusing, right? In and out, but that's all right. So for the wall, the RTH will be not RO divided by RI. I have to use some other subscription, right? So that's the two radius for the wall. Okay, outer radius divided by inner radius for the wall. Okay, that's the log R over R. Okay, 2 pi KL is the same, doesn't matter. Okay, so how about the RTH for the insulation. So that's the log part, right? So for the insulation part, there's also a concentric cylinder, right? It's also just like a ring. Okay, you have an inner radius, outer radius. Again, it will be the outer radius of the insulation divided by inner radius of the insulation. Okay, that's the log part in the numerator. Okay, that makes sense? They're good? Clear? Any question if it's not clear? Okay. So your goal is to find, you have a component, you draw the circuits here. You have 2 layers of materials, right? You draw the circuits. The heat transfer, it's a radial heat transfer. Heat transfer going out like this. So along the heat transfer direction, you have two circuits. There are 2 resistors. One is the wall, okay? The other is the insulation. Okay, so this circuit's drawing, do you understand? So your heat goes through 2 materials, basically. Although it's in the cylindrical coordinate, but it still goes through 2 materials, right? Okay, it's in the radial direction or all the way the same, right? Okay, so the first material the heat goes through is the wall. Okay, and the second material it goes through is the insulation. Okay, so it's a serial configuration. So the first material, the wall, it has a thermal resistance. Okay, the second material, the insulation, it also has its thermal resistance. Your job is to find the thermal resistance of wall as well as of the insulation. Then add them up. Then use this equation. Okay, to find the heat transfer rate. Is that okay? I need some feedback from you. Is that good now? Okay. Okay, now let's look at one example. Of course, when I use example to solve an actual problem, then you probably will be more comfortable with this, right? So the problem we're going to solve is, let's see, example 2.2. On page 32. Okay, it's just exactly this problem. Okay, so you have 2 layers. You have 2 circles, right? 2 layers. First layer and the second layer. Okay, let's read the problem statement. A thick walled tube of stainless steel. Okay, you can have K. Stainless steel. It's a stainless steel pipe, right? You have a K of that. K steel is 19 watt per meter C. Okay, one thing, every time in your quiz, in the calculation, at least the result, you need to provide me the unit. Okay, I probably didn't take points of the first couple. I won't take points for the first couple quiz. Okay, but let me say it early now, from now on. Okay, every time you calculate a value, you need to give me the unit. Okay, you need to write the unit down. Okay. Okay, the inner diameter here, R1. Let's do R1, R2. R1 R2. R1 equal to no, it's D, right? It says D, okay, it's fine. D1 equals 2 centimeter, okay. D2 equals 4 centimeter. So in your log is what? Log R1 over R2. Log RO over R in, right? Is that the same if you put DO over DI? It's the same, right? It's a ratio. RO over RI, you can use DO over DI, diameter. That's the same thing. The ratio is the same, right? Diameter ratio and radius ratio is no difference, okay? So it's okay, we can directly use diameter instead of using R, okay? Not a problem. So this is the inner diameter of the stainless steel pipe. This is outer diameter of the pipe, okay? Okay, it's covered by a asbestos insulation. Are they still doing asbestos insulation? Kind of doubt about it. Okay, so the H is 3 centimeter. Be careful, this is not the diameter, okay? It said it's covered with a 3 centimeter layer of asbestos insulation. So asbestos. Okay, so this layer is asbestos. So you also have the K, let's say Ka equals 0.2 watt meter C. Okay, if the inside wall temperature of the pipe is 600 degrees, so T inside is 600 degrees Celsius, pretty hot, right? Calculate the heat loss per meter of length. Also calculate the tube insulation interface temperature. Okay. So do I have the outer temperature? Do I have T2? Oh, okay, T2 it marked 100 degree, okay. Is this somewhere in the problem statement? It said 100 degree, it didn't. But anyway, in the drawing it says 100 degree. That's probably a typo here. Okay, but anyway, it's given T out is 100 degrees C. Okay, outside is 100, inside is 600. Okay, so it's a stainless steel pipe and it's covered by a asbestos insulation. Okay, so what is the Q? And what is the interface temperature? T, I'm out of letter. Let's say T2. How about that? Okay, so try to find, the goal is, what is a Q? You know there's only one Q, right? And what is the T2? It's the interface temperature. Okay, so how do we do it? Okay, so immediately you draw the circuits for this type of problem. How many items in the circuits? How many resistance? So we exclude the convection, right? There's no convection, okay, in and out. So don't worry about it. This problem is just the conduction only, okay? It's a little bit easier. So you have two components here, okay? One is the pipe wall. One is insulation. So you have a T in here and the T out here. So that's your circuits. Okay. So draw the circuits. It's not the end of the story. They draw the circuit, that's the starting point, right? So based on the circuits, write down that equation for me, okay? What equation? Equation for Q, right? Equals T in minus T out divided by summation of RTA. Just write like this, general equation for me. Show me that you have the correct direction, first step. That gives points, okay? I want to see this equation, okay? So what's next step? I want you to write on the paper. It will be then Q, let me write to this side, equals 600, substitute the values that you have, minus 100, then R, TH, the stainless steel pipe, plus RTH, the asbestos, let's say steel, stainless steel, S. How about that? See, I want you to clearly write down this, okay? Don't worry about writing stuff. Writing down clearly and substitute the value. You know it's 500 degrees. That's so easy. But I prefer you write the 600 minus 100 in corresponding to the equation you have here. Okay, it is this minus this. Okay. Then I give credit from this. Okay, so what's the next step?
The RTHs.
Yeah. RTHS equals, see, that's how I solve the problem. I put it down, divide and conquer my subtasks, okay? So now I know if I calculate RTHS and calculate RTHA, I solve the problem for Q at least, right? Okay, so my subtask is finding this. So what is this? Do you still remember? This is cylindrical, right? It's in the previous page of the notes. What's in the numerator? Don't look at the previous notes.
Numerator and all the other.
The diameter.
The diameter.
Yeah, log.
So I use D1, D2. Is that D2 over D1 or D1 over D2?
D2 over D1.
That's right, D2 over D1, okay. So 4 centimeter over 2 centimeter, right? So it is 2 in there, it's 2 times, okay. So what is the
Can
bottom?
you keep it as centimeter or do we have to transit to meter?
Okay, that's a very good question. I'm very strict on transfer everything into meter, except here. I myself write a centimeter down there. What is the reason? I don't care in this problem.
It's a ratio, so the units cancel.
It's a ratio. It's a unit cancel, exactly, right? So in this kind of situation, if it's a ratio, then it doesn't matter. You use inch over inch. As long as you use the same unit, you're fine. Okay, it's basically log 2. Okay, so 2 pi KL, right? 2 pi K, I have it. K, I have it. Am I? Do I have it? Yes, 19. What meter C? How about L? Let me just keep the L in there. It will be canceled. The L is the same, right? Is that right? See, actually, the problem asks you the calculate the loss per meter of length. Okay, L is 1 meter. Is that right? Okay, so L is just 1. Okay, it should be meter down there. I'm out of space, but doesn't matter. You know, it's meter. It's 1. So, how about for the asbestos part, the log over log? What is it?
Would it be 7 over 4?
Exactly. I cancel out the units. Do you agree, everybody? For the asbestos layer, the inner diameter is 4, The outer diameter is not 3. It's not possible to be 3 outer diameter, right? The thickness is 3. So it's 7 for the outer diameter. Okay. Does that make sense? Okay. 2 pi k, this k is very tiny, 0.2. That's why it's used as insulation, right? Times 1 meter. Okay. That's it, right? These are just keying the calculator. I don't think there's any difficulty after this. Q, let me use the next page. This is the important part. In the test, in the quiz, show me this. You get most of the points, okay? Even your solution is wrong, I don't care. Solution wrong, I maybe take one point off from your 10-point quiz, maybe, okay? So, but majority the part is here, right? Okay. So then do a calculation. Do you have everything else? I think you have, right? R theta, RTH, RTHS, RTHA, you get everything value, right? So you should be able to calculate. So what is the Q? So I guess the Q is, I can just write it to you. 680 watt. Okay. So what's the next question? What is the temperature in between T2? This is just same as our quiz Wednesday, right? In the middle temperature. So what? So you have the Q, which is 680 equals to T2. I think it's T1 minus T2, in minus out, okay? So T in is 600 degree. You can just look at the stainless steel, or you can look at the asbestos, doesn't matter. Either way, you should be able to find the interface temperature. So 600, let's look at the steel. 600 minus the interface temperature, in minus out, right? Divided by RTH of steel. You already calculated the previous, on the previous part, right? And it's equals 680. Remember that Q is the same going through the entire materials. Okay, we share the same Q. So RTH is calculated from the previous page. Do we? RTHS here. Okay, it's calculated. Okay. One thing I want to point out here, for those of you who haven't taken my, or most of you, for those who haven't taken my fluids class, in the fluids class, I emphasized on use those letters, clearly write down those letters instead of writing down those values directly, put it into the equation. If you write down a letter like this, RTHS, so later when you use it, you can go back to find the value you previously calculated, okay? Be really organized and write it down the detail of all those steps and use those letters, okay? Don't be afraid of using those letters, okay? I see many of you just like plugging the value from the beginning, okay? Calculate everything from beginning. To me, you calculate everything at the end, okay? Keep those letters. Then it's serve as a reminder to you later, okay? Now I need a RTHS. Do I have it before? Yes, I did. Okay, I calculated. Okay, so I can directly use.
Dr. Zhang.
That's a good habit, yes.
Can you go back like one or to the previous?
Yeah.
So on your thermal resistance for your asbestos, you're using 7/4.
Yes.
But book is using 5/2, which would be 10/4.
I think it's a typo. It should be, it's an outside layer. It's already 4. The 3 centimeter is outside the pipe. So I think the book is wrong. Okay.
Well, Dr. saying you have to use the diameter you're
Oh, let's see. Okay, I see what you mean. Maybe I made a mistake. Hold on. So R, okay. I can still use R, right? Can I?
yeah, you
Oh,
can use R.
I see. So the radius, I'm using radius here. Okay. Now I got it. So what is the outer diameter? I'm not careful here. So it will be
10.
It will be outer diameter. No, the diameter is 4. 4 plus 6, yes, you're right, it's 10. So what is inner diameter? Inner diameter, it is 4, right? That's why it's 5/2. Okay, good. Thank you for checking on this for me. I indeed miscalculated that. It's 10/4. It's not 7/4. So it's the diameter we're using. So you have a thickness 3 centimeter on one side, both sides you have 6 centimeter total thickness, okay? Is that right? Everybody get it? Good. Okay. So the value, the 680 is correct because I just copied it from the book. Okay. So here it's not 7/4, it's 10/4. Be careful. I make a mistake like this. Yeah, it's possible for you to make the same mistake in the test, right? Okay, be careful. Okay, so now you have this equation. T2 is your only unknown. So the interface temperature is 595.8 degrees Celsius based on this calculation. Okay. Is that good? So in extended to this problem, hey, let's say this, you have this, okay. How about I have a ambient temperature 30 degrees Celsius. How do we do this? I have a heat transfer coefficient here, 50 watt meter square C, okay? Inside temperature is 600 degree. This is not on the textbook, I'm adding this. So this is still the same material, same dimension as the previous problem, okay? So what do we do? Can you calculate the Q? You don't have a 100 degree temperature here. You don't know what's the temperature outer layer. Okay, you have a temperature at the ambient, 30 degree, let's say. Can you calculate this outer temperature to me? Let's say this is T1. What is T1? No, it's not 100. T2. What is T2? Can you do this? Let's say this become a new problem.
Dr. Zhang.
Yes.
Is that H your convection?
Yes, that's a convection
Constant
convection heat transfer coefficient.
Mm.
Okay. This is a more practical situation. You have a pipe, right? You have insulation, then exposed to air. Okay. Then you calculate the surface temperature. Then calculate the interface temperature, T1. Now I get the T1. Previously, T1 is just 100 degrees, right? So what do we do? Can I put this as a quiz? No, come on, I'm kidding. You have 4 minutes only. Okay. Still follow the steps. What is the first step if you do a problem like this?
Is it the same materials as last time?
Yeah, exactly same. Everything is the same. I'm just adding air, which make it more practical. Okay, more reality, right? In reality, it's exposed to air. Okay.
You have to do the conduction equals convection plus radiation thing.
Do this. I told you in the previous example. Do the circuits. Tell me the circuits. Come on, right? Please, every problem in here, you probably draw the circuits first. Okay. You have 3 components on these circuits. This is T inside, which is 600. This is T ambient, which is 30. Can you draw these circuits? Is that right? Do you agree with these circuits? You have a heat transfer going out. Now you go through 3 medias. Is that right? Everybody agree? I really like to see your video, see your face to see if you follow. Okay. Now you have additional medium, which is there. So you have 3 resistance there. Okay. So the first 2 are the same. Right? That's exactly the same as previously you calculated. So you have an additional one. What is the thermal resistance of the air? Oh, okay, I used the A already. Let's say air. Okay, with the knowledge of this, that's it, you solve the problem. Right, is that right? You're still using that equation, right? T in 600 minus 30 T out, which is the T infinite in this case, beginning and the end, divided by summation of R theta, RTH. Okay, so what's your goal? Your goal is trying to find out this, right? In this problem, we're just adding one more circuits there. Okay, this, add this, add this, right? So what is air? It's a convection, 1 over HA. Same thing. We mentioned that last time, right? Okay, that's it. What is the area? Just the surface area, outer surface area, right? Exposed to the air. Okay, so you add 3 together, then you should be able to calculate the heat transfer rate. Okay. Hey guys, did you follow it? If you follow it, it's easy for you. Okay. This is a really, really good process because they make your life much easier. You don't have to think about, hey, heat transfer is same here, conduction, convection. Make it the circuits. Okay. So all the problems now become easy. Nothing difficult. Okay. I guess I'm out of time here. So let's stop in here. I think I posted 3 homework problems on Moodle. Okay. Try to practice that 3 problems. Not many. I don't want to post a lot of problems for you because if I post 30 problems, I'm guaranteed you're not going to do it. Too time consuming, and if I were you, I won't do it. So I give you less problem, but just do it. Make sure you understand. Okay. Do some practice. Okay. I guess that's it for today. Have a good weekend.